So moving on to our next topic is Scott Chevron. He's going to be presenting on reliability in lean manufacturing. Scott brings 25 years of experience in continuous improvement in the manufacturing environment. We're pleased to say that Scott is a part-time employee of the New Tech Group. We bring him in when clients have a need to take a look at their operations, look for the pinch points, the weak points, and how can they drive waste out of their system and push to a continuous improvement environment. Scott holds a BS in chemical engineering and a master's in engineering management. He's a Lean Six Sigma black belt and has certifications in reliability engineering and quality engineering. He also is an 8-year veteran of the United States Navy, so we thank you for your service, Scott. And he has worked for major corporations such as Dentsply, SmithKline, GlaxoSmithKline, yep, and Graham Packaging. In his presentation, Scott will discuss how the Internet of Things overlaps with reliability engineering and describe what reliability engineering is, how it leads to reduced costs, and ultimately improve customer satisfaction. And we'll also discuss how to take advantage of all that data that is now available to us, that you know, there's sensors on everything and it's just accumulating rapidly, but are we collecting the right data, are we collecting the smart data, and then more importantly, how are we interpreting it and to make a more efficient overall system, both within our organization and across our supply chain. So with that, I'd like to introduce Scott Chevron.
Thank you, Andy. All right, good morning, everybody. My name is Scott Chevron and not Kelsey Graham, because I had been told over the years that I look like Fraser Crane. We're not in the basement of Cheers, sorry to tell you that. But we're here to talk today about, as Andy had mentioned, reliability in the Internet of Things. Now, I'm going to say at the top, I'm not an Internet of Things expert. You heard enough of that from Kevin. But it does provide a nice segue to what I'm going to be discussing is how can we take or look at how things are interconnected to these days and looking at the data that a manufacturing operation generates, how that transfer data looks like, and more importantly, what do we need to do with all that information to get the most value out of it? Because I'm sure, just like a lot of other companies, how many of you collect a lot of data every day? Now, my question to all of you is, what do you do with it? Because that seems to be the brunt of a typical manufacturing operation is you collect a lot, and it's good data, hopefully it's valid data, that you could rely upon it and make good quality decisions based upon it. But how often do you really get anything out of it? That's the question. So we're not going to go to a lot of detail about that today, but we're going to talk about some things to think about, especially when it comes to reliability engineering. So how can we look at, we have unscheduled downtime that's beyond our expectations, or if you're doing a line changeover, and a line changeover is longer than the standard. If your standard line changeover time is 2 hours, it's taking you 4 hours, then that's 2 hours of lost production time, less productivity. So specifically, we're going to talk about what is the Internet of Things, not a lot of as much detail as Kevin, but again, to talk about how that's related to the concept of reliability engineering. Why is it important for manufacturing? And why is collecting and analyzing data important for a business? And then once we kind of get that foundational things out of the way, then we'll talk about, well, what do we mean by reliability? What is the definition of reliability? So let me ask all of you, when you hear the term reliability, what does that mean to you? Anybody?
Consistency.
What's that?
Consistency.
Consistency.
Uptime.
Uptime.
Flash.
Anybody else?
Products and spec.
Product and spec. Okay. So those are all good ways to describe reliability. But reliability is about a product and its performance under certain operating conditions for a certain length of time. So that's kind of like the textbook definition of what we mean by reliability. So you not only can look at it as a product and how it survives in the field under field use conditions, but you can also use the concept of reliability in your plant for your manufacturing line. What is reliability management and why is it important? And some common terms. And what are some things to think about with developing a program? And this is where all of us together are going to come up with some ideas. So I've asked them to bring down a pad of paper and a pen, and as a group, we're going to come up with some things that all of you can think about as you leave today and you go back to your plant and you get back to work, are some things to think about to make some improvements. So Andy already covered who I am and what I've done. And as you heard Kevin say, in the last few years, it seems like devices more and more are becoming interconnected, that computer networking systems are talking with each other. Machines on the floor are talking with each other, talking with computer networking systems. You're uploading data from one system to another or transferring it from SAP into other systems in SAP, and all this information is flowing from one source to another. So at home, I have the Nest Learning Thermostat. I also have the Nest Protect. So all these things are connected in a way that if my Nest Protect senses that I have a gas leak by my furnace, it's going to communicate with my Nest Learning Thermostat, and that if my heat is on, my furnace is on, it knows to shut it off. And if you also have smart lighting in your house, you can have your smart lighting flash red if that happens. And all of that is programmable. So much like the smart home, as Kevin spoke about, you also can get into smart manufacturing where certain things happen, and when it reaches this point, it sends a signal to something else, and it causes that system to do something else, and et cetera. And also, collecting and acting upon reliability data has many benefits which have been well documented, right? But knowing where to do that and how to get started in doing that, it seems to be, is always a stumbling point, where people might say, I just don't know what to do. I just don't know how to get started. So as a group, we're going to talk about that as well. This presentation will also discuss how you can take advantage of the new information age and availability data and use it to better manage a product through its life cycle, and as Andy said in the intro, and the ultimate goal is to improve customer satisfaction. So the learning objectives for today is that we'll discuss the overlap between the Internet of Things and the concept of reliability engineering, and hope that you have a better understanding of how to maintain a reliability improvement for a program, to reduce operating a product warranty costs and ultimately improve customer satisfaction. Be familiarized with some really basic reliability engineering terms, and maybe we could talk about what that means to you if you've seen them before, how have you used them, how they work, how have they not worked. And to start building kind of a blueprint, if you will, on how to put a management program together to collect, manage, and as I said before, make the best use of the data that you have right now. So why do we need data? Sometimes, as we said in the intro, a lot of data can be too much data. And again, it probably feels that way because we're not making the best use of the data we collect now. So, but why do we need all that data? Because sometimes it provides a complete picture of how the business is running from one line to another, or the business as a whole. And we heard in Kevin's discussion talking about dashboards, scorecards, et cetera. All that kind of thing helps us drive a business to perform better. And with the Internet of Things and the availability of data, it allows us to make more real-time decisions. So if you think about it, if you have devices, you have sensors that collect all this information real time, it allows you to make decisions faster, knowing real time what's going on right now versus looking at data one day and knowing that it was from the day before, and maybe responding to data the day before is too late. It allows for better and faster problem solving. Now, we would like to think that sometimes we have good systems in place where we have a lot of preventive measures to make sure problems don't happen. But the fact of the matter is, problems happen. And so the idea is to use the data that comes out of our systems, process it using the right tools to make problem solving go smoother and go faster. And with the data, there is the hope that we understand the cause and effect relationship between the data that we collect. So what do I mean by that? So anytime that we have a problem of some kind, if you remember back in your math days, it's as simple as saying y is a function of x. Y is simply the thing that we're measuring that comes out of the system. Think of any data that you collect where the output is some measurement. But that measurement is a function of everything else that goes into it. So y is my output, x is the input. That's everything else that's built into your system. Your gauge R&R for your measuring devices, that's an input. People are an input. Age of equipment is an input. How you maintain your systems, the maintainability is an input. There's a lot of factors that make up this input. But the question is, when you're trying to wrap your head around all this data, how are these inputs interrelated, and how do they impact the output together? So a good example would be medication. There's a reason why doctors ask you, what other medication you're on. They're asking you because they want to make sure that there's no severe interactions, right? Well, collecting data in your facility is the same way, because there could be multiple things going on at the same time that were only when they're together at the right levels that could impact that output in only one specific way. So collecting the right information, analyzing it the right way is very valuable. Any questions so far? Okay. Now, this concept of big data and the internet thing is a great partnership. But sometimes, when you look at the amount of data that a system sometimes collects, is overwhelming. And processing it and making something meaningful out of it is what I call it analysis by paralysis. Right? Sometimes too much data is not a good thing, right? So Kevin already talked about what the Internet of Things is, and again, it's about the interconnectivity of devices and how information is transferred from one device to another. And it's all about, and we're talking about manufacturing now, and again, it's about sharing information, processing it, and allowing the business to make better decisions, faster decisions, based upon this interconnectivity. And from what I saw, and again, it's kind of mixed results, this idea of the Internet of Things, the concept was developed in 1999, believe it or not. But as Kevin has talked about, the evolution of this concept of Internet of Things is on this 4th generation, and as time goes by, we're gonna see higher stages of evolution. Who knows, in a couple of years, we might be calling it 5.0. So why should we think about IoT manufacturing? And the first two are what I'm going to really focus on from this point forward, is the idea of how Internet of Things in manufacturing could lead to better product design. So let's think of a race car. So when a race car is developed, they go through many iterations of the design. They have all these different sensors hooked up to a car that's monitoring everything imaginable. Exhaust levels, gas levels, et cetera, measuring temperatures, pressures, and they use all that information. All these devices are connected because they say, oh, if we turn this dial one way, let's see how the system responds. Or if we turn this and this at the same time, how does our system respond? And it's all about the end goal of making a better race car. So those knobs I'm talking about turning are the inputs to any process. You think of any machine on the floor, every time you're turning the knob, adjusting temperatures, pressures, belt speeds, whatever you may have, those are all process inputs that you're changing. How they impact the big Y is what the goal is. How can we improve Y by controlling the X's? So it also helps with better product lifecycle management, or PLM. And what that means is ultimately the product in the end user's hands. How does it survive under usage conditions? Because that's the end game when we're talking about reliability engineering, is when the end product is in the customer's hands under customer use conditions, is it lasting as long as we say it will? If it doesn't, then that means there's warranty costs involved. Warranty cost is a cost of doing business, and the idea is over time, minimize the amount of cost, the cost of business because of a product lifecycle issue. Now, but what I mean by product lifecycle and better product design also is in the product development process, we're talking at the very beginning, what testing, reliability testing is being done to not only prove that it can survive in user conditions, but how can end users misuse the device, whatever that means to your business. And then the idea is through accelerated testing in the product development lifecycle at the beginning is how can we test the devices at those awkward conditions where people can misuse a product, but it could still survive up to the amount of time that we say or claim it will be. That is a challenge. And one graph I found online, it was an online article found in Industry Week. Basically, this graph shows that within the next 5 years, we can expect the level of depth of visibility today to have more involvement with the supply chain real-time orchestration. There was a lot of questions for Kevin about supply chain, and it sounded like we're not quite sure where we're going, how we're going to get there, when we're going to get there, what it's going to look like. But everybody believes that having an integrated supply chain, have it be automated, is going to be the biggest thing that we're going to see in the next 5 years. Slowly move away from being offline meaning managing via Excel, or maybe taking Excel spreadsheets and loading them up in SAP. If you ever been involved with that, it could be quite a hassle. But to have real-time supply chain integration, we're getting low in this supply, the system recognizes it, contacts the supplier, it says we need this SKU, this many of that SKU, and et cetera. So, and it all ties into this concept of smart manufacturing. It's about creating an environment where all available information within the plant floor and the supply chain is captured in real time, made visible, and turned into actionable insights. And the key word here is actionable, I think. Because what's the point of collecting data and having all these integrated systems if you're not looking at what it's telling you and responding to it? So that's kind of the key, is if you're going to collect the data, make it actionable data. All right, so that was kind of why data was important, kind of rehashing this Internet of Things concept of why collecting data is important. But there's a fine balance between collecting the right data and making use of it versus collecting everything and doing nothing with it. So there is a big difference between the two. So are there any questions so far? Okay. Now we'll kind of move into the reliability side of things. So the kind of textbook definition of reliability is the duration or probability of failure-free performance under stated conditions. The probability that an IA performs its intended function for a specified interval under stated conditions. So can anybody give me an example of a product that some of you make that you can give us an example of a reliability definition? Like under blank, blank, blank conditions, product should last 6 months, 1 year, I don't know, whatever it is. Any examples? Yes, sir.
Our customer, we make Cat 6 connectors,
Okay.
and our customer guarantees them for 30 years.
Okay. But under
No matter
what
how-
kind of conditions?
No matter how many times
Okay.
you made them, unmade them, 30 years,
30 years. Okay.
which drives a beryllium copper instead of a phosphoide.
Okay, so for that example, anything less than 30 years is considered a failure,
It is.
right? And there's a cost of the failure from paying for shipping back, processing the warranty claims, and if the problem becomes too much for anybody, then something that could affect you is what's called loss of customer goodwill if you have too many returns, or if you're in a more heavily regulated industry where you have to do a formal product recall. I mean, you're talking, you could be losing millions of dollars under those circumstances. Thank you for the example. But you can use this concept of reliability from multiple perspectives. Number one, it's about the end product itself. That's the more common example. But you could also talk about equipment reliability, one piece of machinery in a manufacturing line, or a manufacturing line as a whole. Looking at the reliability of a line, or for particular equipment, you could talk about the reliability of an individual component within a machine, like gears, every component of a machine. Now, what's interesting though is when things fail on a machine, they fail for a reason. Maybe it's just wear out. Maybe it gets to the point where it becomes to the end of its useful life and it just needs to be replaced. But sometimes things break when we don't expect it to break. Every component of a machine has what's called a mean time to failure. So when your suppliers make parts for you and they give them to you, they also have an expected reliability. But often, as manufacturers, we don't necessarily always know what that is. So that's something that might be worth asking your suppliers is, what's the reliability of blank piece of a component for your machinery? Because ultimately what that means is the individual reliabilities in that machine dictates the overall reliability of that machine. And it's serial. So if you have 100 different components in a piece of equipment, and they all have, let's say, 99% reliability, then 0.99 to the 100th is the reliability of that piece of machinery. And that's saying that's the best you're going to do. So what does that mean? Sometimes it means looking at the life cycle of a component for a piece of machinery, understanding how long it's supposed to last, and developing your maintenance plan around those individual components with the highest risk or the lowest reliabilities. Because you know that with all the reliabilities of all your components, that 0.99 to the 100th is the best you're going to do for that piece of machinery based upon those individual components. Now, that's not to say every component will have a 99% reliability. It could be less. It could be more. It could be 99.5. Who really knows? But the idea is that if you ask your suppliers, you can see if they have this information. If they have that information, then you can start getting a little bit better on tailoring your maintenance program. Does it need to be predictive maintenance? Does it need to be corrective maintenance? Does it need to be preventive maintenance? Do you have autonomous maintenance? So there's a lot of questions you can answer based upon the availability of that data and what you do with it. So what are the benefits of having, let's just call this umbrella program of reliability management? Number one, ensures actual product design meets customer specs. Sounds kind of silly, right? But I have seen cases where a product was designed beautifully, but the customer doesn't want it, or we can't manufacture it. Likewise, maybe it was a bad product design and we tried to manufacture a bad product design. It happens, guys. So how do you incorporate, how do you make sure that product design matches customer specs, that the product design can be manufactured and be manufactured to those product specs? And that's by having a good reliability management program that provides less waste. Who's familiar with the term value added or non-value added? Okay. So, so there are kind of 7 traditional activities that are considered non-value added. Number 1 is defects. So anytime that you produce or generate something that you don't expect, that's considered a defect. So let's suppose your goal for quality is a 95% first pass yield, and you only had 85. Well, you had more waste than you budgeted. That's a waste, a defect. Oh, overproduction. That means you've made too much. Inventory levels are supposed to be here, and you're carrying this much. The overage on in-house inventory is considered waste, and there's a cost that comes with carrying too much inventory, right? Number 3, transportation. Anytime you move things and customer is not willing to pay for all that movement, and I don't mean necessarily internal, it could be external. Like if you have a secondary warehouse off-site because you don't have room in your current warehouse, all that movement back and forth is considered transportation waste. Your customer's not paying for that. By definition, that's considered waste. Waiting. Any time between process steps where one process step is waiting for the previous to be done is considered wasteful. 5th one, inventory. Again, inventory by definition, if it's more than expected, more than budget, more than standard, that's considered waste, and it comes to a cost of the business. Number 6, motion. Think of motion as ergonomic type activities, meaning twisting, turning, bending, whatever, or within a work cell, moving from one place to another many times during a shift. That's considered wasteful. And the last one is P, is processing. So in other words, if it's supposed to take me 5 steps to make something, but I'm really taking 8, I'm over processing, probably doing too much that's required to make that part. So by having a good reliability management program and thinking of all these things ahead of time, it produces less waste. Increased line uptime and decreased line changeover time. So when I asked what the definition of reliability meant to you, I believe one person said uptime. Who was that? Yeah, uptime, right? So we could have more line time and decreased line changeover time because of the concept of reliability. We can reduce external failure costs. We kind of talked about that with this gentleman's example up here. So not only have reduced external failure costs, which are warranty returns, recalls, loss of customer goodwill, but you could also have decreased internal costs. If you have rework, spoilage, you have less defects, inventory carrying costs, those are all examples of internal failure costs. And again, those are all costs to the business, right? And also, having a good reliability management program is a precursor to also reducing incidents. So if you design a good workspace and you look at all the different elements of reliability engineering, it can help reduce the incident rates of a facility. It can only help with safety. So are there any questions so far? All right, some basic terminology. Now, there's not enough time to talk about every single definition that exists in the world of reliability engineering management. But I looked at the ones that were available and I thought, well, if I list 3 or 4, that's probably a good start to give you an idea of what's out there. First one is availability. And this is the long, boring textbook definition. A measure of the degree to which an item is in the operable and committable state at the start of a mission, when the mission is called for an unknown reign of time. Now, you could translate that to mean if the machine is supposed to be available for 20 hours today, how long is it actually available? Right? So if there's 24 hours in a day, and let's suppose I scheduled 4 hours for maintenance, 1 hour for breaks. So the availability of my machine is 19. If I only run 18 hours a day, 18 divided by 19 is my percent availability for that piece of equipment. The availability measure is part of this bigger picture measure called OEE. Operational Equipment Effectiveness. And there's 3 components of MOEE. Availability, quality, and what's the other one? I see some people nodding. What's that?
Efficiency alone, the cycle time.
Cycle time, right. So, and that means the standard run rate. So if a machine is supposed to run 1,000 parts an hour, and you're running 900 parts per hour, your rate is 90%. And this measure is cumulative between those 3 metrics. So if I have a quality of 90, an availability of 90, and a rate of 90, my operational efficiency is only 72%. Now, on a scale of 100, if you're not familiar with this metric, you're probably looking at that and thinking, wow, you know what, that's not really that good on a scale of 100. But for this metric, for most pieces of equipment, for most industries, a kind of a benchmark, if you will, is considered 85% for that cumulative rate there. So how many of you use that as a primary metric for manufacturing? Anybody? OEE? Okay.
Can you repeat what that means again?
Operational Equipment Effectiveness. At some other terms, mean time between failure, mean time to failure. Kind of sounds like it's the same thing, and it really is, but there's one key difference. Whether or not the device, the system, the machine is considered repairable or not. So if it's a one and done thing where it fails and you can't fix it and put it back in service, then you would use the term mean time to failure. But if it's something that fails, you can swap a component out, put it in, and consider it to be almost brand new, if you will, then that would be mean time between failures. Now what's interesting about these terms is that every time you have a failure, let's say it's in reliability testing on a new product, a piece of machinery, or data from the field on how long it's surviving in the field, all of those things can be modeled using statistics. And the way to get an understanding of that is you can easily model. And the way you model is based upon the mode of failure. So if you determined a mode of failure to be will wear out, the component got old, then you would label that data point as wear out, or any other root cause that you come up with. But the idea is for every failure mode, you can model what the failure rate is. And if you can model the failure rate of your components for a manufacturing line or the parts of the machine, you can adjust your maintenance programs based upon that kind of data. And that's kind of ultimately where we want to go to is, are we doing maintenance at the intervals we need to? If we're not, why are we not? Making decisions, changing maintenance frequency should be based upon data. Making decisions, important business decisions, should be made with data as much as you can. And collect as much information about data as you can. So when I talked before about inputs to a system or machine, it could mean a lot of different things. So I worked for Graham Packaging for 5 years. I worked in their corporate quality department as a Six Sigma Black Belt. I would have to do analysis all the time in support of our different plants and manufacturing. And so an example of what I mean by have as much data as you can in the categories is I could have a bottle. I won't use your bottle, I'll use mine. I have a bottle, and there's many different dimensions of this bottle that I can measure. But it's also a function of where it comes from on the machine. Let's say it comes from the right side of the machine, the left side of the machine, or if I look at the bottom, I can see which cavity it came from. There's lots of different ways that I can identify that one piece of data. So why is that important? Because when I'm troubleshooting, when I'm trying to figure out why my variation is too high, or why my measurement is off target, every little bit of detail that I can get my hands on will help me identify what the real issue is. So if you think of things that you make where you're collecting data, again, think about how much more you can collect to make that data more meaningful. Again, in this case, which cavity it came from, which machine it came from, which side of the machine it came from. I would also be able to tell which side of the trimmer it got trimmed on. And so now, with a little bit more detail, I can get to the root cause faster than I could before if I collect just a little bit more information. So, any questions so far? You're all awake, so that's a good thing. Yes, sir.
Yeah, but just on the operating equipment efficiency, do you find most manufacturers for the availability, like if you're running a 24-hour operation, do you schedule the 24 or only use the load on the machine? If the machine only has 10 hours a day load, do you use the 10 or do you use the 24? What do you find most manufacturers do?
In cases like that, because in cases like that, we're talking about that there's a not enough business to keep the machine
Correct.
running. So you would use the 24. Because the idea is to challenge yourself to get more runtime.
So you would use 24, even though, I mean, that really goes back to sales, marketing, whatever.
Right.
There's not enough load, so you would use 24.
Well, okay, I've seen it both ways. So then if you wanted to take that time out, then you would say for availability would be 24 minus loss of business minus if you're doing scheduled maintenance minus breaks, whatever, divided by 24. So, it could be most of the time when I do my data analysis, the biggest room for improvement is always quality and availability. Quality kind of speaks for itself. But availability, I mean, I made it more simplified than it really is, but availability also takes into account unscheduled downtime, because you have to take that into account too. You're expected to run 20 hours a day, and you had line issues, maybe it was because of a startup, maybe it was because of something else, and you only ran 16 hours that day because of unscheduled downtime. That gets factored in there as well. And that's where most efficiency numbers take a hit, is because of quality and availability. Usually, the rate is never an issue. You're expected to run 100 parts a minute, 100 parts a minute, or maybe 105 parts per minute. But it's usually quality and availability are the things that drag down that number.
Unless, of course, it's a manual operation. Your availability for your rate can become an issue because it's not controlled yet. It's human.
Right. So in cases like that, it's about studying, putting in place standard work, and making sure everybody is well, it's also the standard work and the rate at which they work is also based on customer demand or the tact for that particular day, for that particular shift, whatever. And making sure that you're staffed appropriately, that everybody's trained properly on how to work in that work cell, how to, what their standard work looks like. Because I've seen situations where, for manual operations, that the customer demand changes day to day, which means for a particular work cell, your staffing might change from day to day. Instead of one person, it might be 2 people, or 3 people, and the workflow scenario for each of those situations has to be different, because the staffing is different, the expectations within that cell and what they're doing is different. So for that situation, you would look at the number of people needed for a particular work area equals the tact time divided by the cycle time. And the tact is the rate at which the customer demand is coming in for that day. So let's suppose hypothetically that for a given work cell, or for a given day, I'm just making numbers up. Let's say it's 100 parts a day is the demand. And, or let's say, I don't know, let's just keep it simpler. 100 parts per minute. Okay, let's say it's 100 parts per minute. And the cycle time to do that one process step is 50 minutes. Then number of people needed is how many? 2. So if you have a variable demand schedule, then you can easily figure out how many people per day you need to meet that demand. But in order to do that, you need to have a standard work plan around that variation in customer demand. To say, if I have 1 people, this is what the workflow looks like. If I need 2 people, this person's going to be doing this, this person's going to be doing that. For 3 people, or etc. Did that help?
Yeah.
And the last term is the mean time to repair. So think of that as your piece of machinery goes down, and how long does it take to get back up in service? Now, for some of you, it may mean different things. When does that clock start? When does that clock start versus when does the clock stop? Defines that mean time to repair. For some businesses, the stop time means that the repair was made, the line is up running, and you have to do some kind of line verification or any other quality checks to make sure you're good, and then that time officially stops. So it varies for different people. But again, mean time to repair is another measure that you can do that analysis on to see, are you getting better or not? And you can also base it upon what type of repair. Was it due to unscheduled downtime? Was it due to scheduled downtime? Was it due to a component of the machine breaking? Or was it something else? But there's a lot of ways you can put your hands on data to model. You can model just about anything. But the idea is, if you're going to do that and you get the results, then you need to do something with those results and not just go, oh well. All right. So looking at the time, we're doing really good on time. Probably need about 5 or 7 more minutes, then we'll do some basic Q&A. I mean, we've had a lot of great questions so far. And then we'll stop around 10:30. So what are the keys to a reliability management program? Now, you may see, online in the literature, some things that are common, what I put down. This is what I believe is needed to manage a good reliability program. And number 1 is supplier management. So again, think of the term reliability engineering, or think of the term reliability. We said it was having a product under stated conditions last until a certain time, whatever we define that to be. And you look at all of the potential reasons. So if I'm thinking of my y as a function of x, I'm looking at what are all the things, all the reasons why I could not meet my reliability goals. All those reasons are my inputs, my little x's. So if I were to ask, what are the things that can go wrong, if you will, that prevents me from having a good product design, that I can manufacture it, and then it can last in the field as long as I think it can. Having a good supplier management program, I think, is key. And how can you go about doing that? Number one, a SCAR, Supplier Corrective Action Request. How good are you at identifying an internal problem that you tie to your supplier, communicating with your supplier on that item, and making sure that they're doing root cause analysis on their side to explain why they sent you a bad part. Auditing. The question then is a supplier a certified supplier? And what that means to you. Do you have auditors, or do you have people that go to your suppliers and audit your suppliers to some standard? Or do you accept incoming parts from your supplier, maybe with a C of A, certificate of analysis, saying that it's good? If you're having problems, I'm just saying these are some questions you should ask. Inspection plans and AQLs. So when you have your incoming material coming in, how are you inspecting it? Are you inspecting it? Are you looking at the C of A's and saying, hey, you know what, they've been a good supplier, this is good enough, and that's okay, that's fine. Our inspection plans are based upon supplier history, among other things. But if you have somebody who gives you bad stuff all the time, then putting them on some kind of inspection plan internal to you is probably a good idea. And AQL is called acceptable quality limit. It's kind of a means to which you can develop a good supplier inspection plan. MRB, Material Review Board. So internally, do you have a process where if a part fails that came from your supplier, do you have a team of people that sit around and talk about these failed components, and how are you going to interact with your suppliers, maybe in the form of a SCAR, maybe it's in the form of just a casual email or call? Is there a process in which you're looking at failed components that you are getting? And lastly, as I mentioned before, supplier performance and history. Some companies have supplier quality awards, a very formal program where they identify their good suppliers based upon some criteria. Or do you have a supplier dashboard that you can instantly look at to see who the better suppliers are or not? Or for a given component, how many approved suppliers do you have? Do you have only one person? If they go belly up, what are you going to do? Or sometimes there's one supplier in the world, and you just have to deal with how they're doing. And maybe there's not a chance or an alternative supplier. Product lifecycle management. Is there a design process? Is there a stage gate process where every aspect of the design, you're doing stage gate reviews, you're constantly looking at the design and whether it's manufacturable and it's a design that your customer or end user really wants. The life cycle needs to be risk-based. And by risk-based, the most commonly used tool is called an FMEA. Who's heard of that term before? Okay, for those who haven't, FMEA stands for Failure Mode Effect Analysis. And there's many different ways in which you can do an FMEA. One is you can do a product FMEA that specifically looks at the design of a product and how that product can fail, assuming that the manufacturing process that's going to be used is the right process. The process FMEA looks at the entire process from beginning to end, assuming that the product design meets customer expectations. So, RiskBased. In your development, involve the suppliers. Engage your suppliers early in the development lifecycle, get them involved, as well as maybe getting in some of your end users. Work with your product marketing team, focus groups, and start to have iterative processes with people during that cycle. Make sure the product is manufacturable. Also take into consideration deviation management. What that means is a deviation is simply you expect something to happen, but you get different results. And so now you have to question whether or not you need to write a deviation to say, well, yeah, it's not what I expect. Okay, let's send it through. Or, you know what? I really got to stick to my guns here. We really need to be stringent upon this spec, whatever it might be. But you have to have a system in place that handles deviations, what to do with them, how to manage them, how to close them, etc. And warranty analysis. Again, if a product doesn't meet in-use conditions, how are you going to process warranties? How much is it going to cost? Maintenance planning. What is the best maintenance strategy given the components you use? Is it preventive maintenance? Is it corrective maintenance? Is it predictive maintenance? One lean tool is called autonomous maintenance. What maintenance can I put in my operator's hands every day that they can do themselves and not have to get the maintenance team out on the floor? Because maintenance should be a strategic asset, a strategic program for a company, rather than, okay, let's just send them out to fix everything. There are some things that normal operators should be able to do, and we should allow them to do that with the right training. Total productive maintenance, parts control and inventory, parts procurement, those are all part of what I call the maintenance planning or maintenance cycle, and being able to do that well. Do you walk into your part storeroom and it's a disaster? Or do you walk in and you know where things are, maybe using updated technology? You look and say, oh, I only have 2 of these, I need to order 5 more, bam, I just ordered it. And there's a lot of simple ways that you could make that work well. A trained workforce. Knowing why is half the battle, is the way I like to call it. As adult learners, as adults, a lot of times when we need to learn something new, of course there will be some people that will push back for different reasons. But a lot of times people, workers on the floor, they just want to know, why do you want me to do this? Why do I need to change? Why do I need to do things different? A lot of times, knowing is half the battle. I mean, we would like people to comply and to do it well. I totally get that. But knowing why we want them to do things and why it's important, what the big picture is, a lot of times most people just become compliant then. That's what we need to start with. We need thinkers, not robots. Right? But, we talked about the Internet of Things and that some things are going to be automated, but we're still going to need people. People are still going to be part of the equation. But we want people who can think on their feet. We don't want somebody who just has to go over, push a button, stand there and watch things. We want them to be an active participant, to problem solve, to think, to make things better. There are some companies that have a training budget. I work for a big pharma company. They had a training budget where they felt training people multiple times a year, maybe on the same thing, maybe on different things, was an important aspect to their daily life. And also, just continuously improve. Always strive to get better. Always look for ways to do things differently, to think differently. And of course, top-down leadership. Putting the message out there that these things are important. These are the reasons why. It's not we're going to do things this way. You got to pull people along to get them to understand why change is necessary. And I think that's all I had. Are there any questions? If you can't think of any now, that's okay. There's going to be a lot of opportunities throughout the day. Or you have my contact information. I'd be more than happy to. Yes? Hi.
So OEE like measures, I mean, it's equipment effectiveness, right? But like when you talk about people, we run into like a lot of situations that people aren't really measuring the resources that well. Like there's soft touches that people are doing throughout the day and they're affecting the availability. So the machine can know what its OEE is of that machine. We can look at the line. You see a lot of people saying, my line OEE is this. And it's like, is that true? Then you see some people, I mean, because like it doesn't take into account the people side of it, effectiveness of the people, effectiveness of the system, the work cell.
It would be rate. If it was making rate, the machine would know it.
So
a lot of companies like to tell themselves. A lot of companies like to tell themselves the OE is only that. But the truth of the matter is, it's also the quality of the product. And I've worked with companies where they said the OE is X, and it was actually inflated because they weren't taking into consideration the quality. And that's usually what drags the OE down.
So globally, like how's that affect? Like how do we get on the same plane, like level? I don't know. This kind of question.
I mean, OEE is a standard definition. It should include rate, availability, and quality. So if somebody's calling it differently, you know,
Yeah. Okay. So
they just
do you see this?
need the. No, I've never seen that as a problem. But what I have seen as a problem is, like when I was with brand packaging, I worked in corporate quality, and a lot of times I will get our OEE at this plant is blank. We need help figuring out how to improve it to this level. Okay, so what do? I go where the data is. I log into SAP. I pull data from the plant by shift, by line, as much detail as I can get, and I do an initial analysis. And then I'll go to whomever requested help, and I'll say, this is what the data is telling me. And a lot of times it was, for some of the measures, usually rate was like this, quality, and a little bit of wiggle, but it was mostly the availability, was all over the place. So I would say, here's what I see, here's what I think we need to do next. And I can do all that remotely without stepping foot in the plant. This is just what I see right now. And sometimes I hear, well, that data is no good. So the struggle then is, and this is everywhere I've seen it, is, well, how can you make decisions on bad data? And you can't, right? So the question is, well, how do we get good data then? Because sometimes it's manual. At the end of a shift, the production supervisor goes into SAP or goes into some spreadsheet. He's putting all this information in. If they're not all doing it the right way or the same way, then yes, you're going to get inconsistencies. You're going to get inflated or overinflated numbers. And so everybody has to be on the same page. Then you need that top level leadership then, the production manager, the plant manager, whomever, to say, we need to have consistent data. We need to make sure that everybody's doing it the right way all the time. Get the people involved that have to do this activity and say, well, how can we do this differently? We need to do this. This is not like we're not going to do it anymore. But how can we do it better so that we can have more reliable, actionable information? And that's kind of the key, is how to make your data valid. But that involves the people component, right? Because there are some companies where they're a typical plant, your average line worker gets quarterly bonus, monthly bonus, annual bonus. And it's based upon a lot of things: safety, quality, productivity. Yeah, you're going to get some people who are going to call things better than they really are, because there's something something at stake. So there's the whole cultural element now on how to deal with overinflation of numbers, which that could be quite challenging as well.